In chapter 26, we're going to start our study about light. Of course, light's crucial. We get most of our information about the environment either through sound waves, what we hear, or through light, what we see. All light begins with a vibrating or a moving electric charge. If you have a vibrating electric charge, it's going to set up an electric field that also vibrates or oscillates. So if you have a vibrating electric charge, you end up getting an electric field that looks something like this. It looks like a wave. Interestingly enough, anytime you have an electric field that varies, and we haven't talked about magnets yet, but a varying electric field causes a magnetic field that varies, and that magnetic field will be perpendicular to the electric field. So if this electric field is going up and down like this, the magnetic field is going to actually be sticking out of my board like this. Can't really draw it that well, but I'm going to try. So this was the axis. It'll look something like this. Where the red is coming out of the board, that's my magnetic field. So as long as we have a vibrating electric charge, it creates this changing electric field, and a changing electric field generates a changing magnetic field. And what you get is a self-propagating electromagnetic wave. It's important that you understand that the electric field is perpendicular to the magnetic field, but both of those are perpendicular to the direction that the wave travels. Our wave travel, or our velocity, would be in this direction. Now, the speed that these electromagnetic waves travel was first determined by a man named James Maxwell. James Maxwell did for electricity and magnetism what Isaac Newton did for motion and gravity. He came up with Maxwell's 4 laws, or 4 equations, that describe all the characteristics of electricity and magnetism. This was a major, big deal breakthrough. But just like Newton used the work of Galileo and Kepler when he came up with the laws of motion and the law of universal gravitation, Maxwell's equations individually, one of them is Faraday's equation, one of them is Ampere's equation, another one is Gauss's law. Don't remember the name of the 4th one. But my point being, he didn't come up with them, but he pulled it all together to get this cohesive explanation. And one of the things that came out of his work is that electromagnetic waves should travel at a velocity of 300 million meters per second. That was based on the constants that are in those laws. Interestingly enough, experimentally, we already knew that light traveled at about 300 million meters per second, or easier to write it in scientific notation, 3 times 10 to the 8th meters per second. So this was a major clue that light was an electromagnetic wave. What light actually is has been debated for a long time. We now know, I'm getting a little ahead of myself, but it has wave characteristics and it has particle characteristics. We call this wave-particle duality. We're going to talk about the electromagnetic waves primarily, but we'll also mention this idea of photons, or little bundles of energy, or little bundles of light. Okay, so these equations said electromagnetic waves should travel at this speed. Light happens to travel at this speed, so it gave us the idea that's since been substantiated that light is a type of electromagnetic wave. But visible light, the light that you see and the light that we think about, is not the only electromagnetic wave. Okay. This is not in the PowerPoint, but this is something that I've used in my classes a lot to help people remember the electromagnetic spectrum. We use red Martians invented, very unusual X games. Those letters of red Martians invented very unusual X games tell us the order of the electromagnetic spectrum and the different types of electromagnetic radiation that we talk about. I'm going to give kind of a brief overlay of all of them, but I'll go ahead and tell you what they stand for. R is for radio waves. Radio waves are exactly what you think they are. Broadcast radio stations emit electromagnetic rays or electromagnetic radiation. If your favorite station is, this is the only one I know off the top of my head, PHYS 105.1, it broadcasts at 105.1 megahertz. This is the frequency of the broadcast. Mega means million, so it's 105.1 million hertz. Or, if I want to write that out the long way, so regardless of whether you listen to 95.5 or 88.9 or 90.1, if it's an FM station, it's in megahertz, and that's its broadcast frequency. AM stations have slightly lower frequencies. They broadcast in kilohertz. The M stands for microwaves. They do exactly what you think they do. If they're in a microwave oven, they heat up your food. But the other thing that microwaves do is that's what's used for cell phone signals. Cell phone towers broadcast in microwave signals. I is for infrared. Notice the color red, because the infrared is the part of the electromagnetic spectrum that has frequencies that are just below the frequency of visible light, or just below the frequency of red light. We detect infrared radiation as heat. That part of the sunlight that reaches us, we get infrared radiation from the sun, we get visible light, and we get UV radiation. The infrared radiation is the part that warms us. Infrared radiation is used for like night vision goggles. The other place we use it is in remote controls. If you've got a remote for your television, it's probably using an infrared signal. If you have a radio-controlled toy car, it's probably using an infrared signal. So we've talked about radio waves, microwaves, infrared. Now for the V. The V stands for visible light. It is actually the smallest part of the electromagnetic spectrum. And generally speaking, while we're talking about the electromagnetic spectrum, all of these can be considered types of radiation. An electromagnetic wave is radiation. However, we consider visible light to be extremely safe. Infrared radiation, heat, we need warmth. Microwaves and radio waves are also considered to be really fairly safe for a couple of reasons. One, they're low frequency. Low frequency means they carry less energy. The other reason is they're really big. A radio wave might be 3 or 4 meters long. Well, if you think about it, that cannot get inside the nucleus of a cell to do cellular damage. That's where we start getting in trouble with radiation. So we'll kind of come back to that when we get to the other side of visible light. Visible light can be broken down into a spectrum itself, and you should probably notice the lowest energy, longest wavelength, and we'll talk about it next chapter 2 with color, is red. And the spectrum goes from red to orange to yellow to green to blue, then violet. You may have learned Rory G. Biv, but I don't usually include indigo because blue and violet pretty much covers, those are our primary colors we think of if we're buying water paints. They're not the primary colors of light per se, but that's our spectrum. Those are the colors in the rainbow. Again, this end down here is low frequency. And by the time you get all the way to the X games at this high other end, we're at high frequency. Okay, so what we're learning is the part of the electromagnetic spectrum that we actually see is very, very, very small. Actually, very unusual X games. Okay, the U for unusual is ultraviolet. We often call this UV radiation. Notice ultraviolet has a frequency just higher than violet. So infrared is just below red. Ultraviolet is just above violet. The sun does give us a lot of ultraviolet radiation. The atmosphere blocks out quite a bit of it, but we still get enough of it that it can cause skin cancers. Okay. Now we're getting into this part above visible light where we have higher frequency, higher energy waves, but they also have much smaller wavelengths, allowing them to penetrate more into the skin and do more harm. These are the rays that cause sunburn. X is for X-rays. X-rays are potentially both very helpful and damaging. They're used for medical diagnostics. If you need to know if you broke a bone, you want an X-ray. On the other hand, X-ray exposure can cause genetic damage. It can cause cell mutations. And then our last one, and the most dangerous, are gamma rays. Gamma rays are very high frequency radiation. They have very, very small wavelengths. Those are the rays that we associate with nuclear reactions. Okay. Fortunately for us, most of the gamma rays that would be coming from the sun, they don't get past our atmosphere. When you hear people talking about the ozone layer, remember, we do need our atmosphere, we do need our ozone layer to protect us from all these high energy forms of radiation. Transparent materials transmit light. Now, when we think of transparent materials, we're normally talking about visible light. So for right now, we'll talk about visible light. But you might stop and think that there are some materials that would allow certain types of electromagnetic radiation to penetrate and yet block other forms of electromagnetic radiation. So they may be transparent to certain frequencies and not transparent to other frequencies. Okay? We know that clear glass is transparent to visible light. There's a diagram in your PowerPoint, but basically what happens if you have a pane of glass, and in here are these different atoms making up the glass. And that's not nearly enough, so let me draw some more. Let me make it very exaggerated. Okay. Remember how I said that light is a wave, but light is also a particle? That's one of our big mysteries, but we know it's true and we accept it. It's called wave-particle duality. Light is made up of little bundles of energy we call those little bundles of energy photons. So when your light ray, here's our light coming in, shines on this, basically this absorbs a proton. When you absorb a proton, you gain a little energy, you get a little bit excited, and then it spits the photon out. And then something else gains that photon, and then it spits that photon out. And another atom gains a photon, and it spits that photon out. And finally, the wave makes it through the transparent glass. In fact, it'll even come through going at the same angle that it was going. But all of that absorbing photons and releasing photons and absorbing photons and releasing photons takes time. But what we find is electromagnetic radiation slows down when it has to travel through a medium. It's fastest in a vacuum. It's really kind of very different than a mechanical wave that has to have a medium. And in a mechanical wave, generally the denser the medium, the faster that sound wave will travel. It's exactly almost the opposite for light. The denser the medium, the harder it is for the light wave to travel through it. If we're talking about air, in a vacuum, let's just say, we know that light travels at c. And we know C is 3 times 10 to the 8th meters per second. If we go into something like water, water is a transparent medium, and it slows it down. It'll travel at about 0.75 C, about 3/4 of the speed of light, or 2.25 times 10 to the 8th. Depends on the glass. The glass typically is going to be somewhere around 0.67, about 2/3 of the speed of light. So instead of 3 times 10 to the 8th, it's more like 2 times 10 to the 8th. And finally, if you get to something very, very dense, a diamond is very dense, one of the hardest known transparent things. It slows down to like 0.41 C, so less than half of the speed of light in a vacuum. Okay. So light travels through transparent materials, but when it travels through them, the speed changes. Well, that's true of other types of waves. Remember, how fast a wave travels depends on the medium. Okay, so for transparent mediums, you can see it will always travel just a fraction of the speed of light. The fact that it travels so slow in a diamond is one of the reasons diamonds are sparkly. It's not the only reason, but that contributes the fact that that light slows down. Now, whether or not a material is transparent depends on the radiation that's trying to get through. We know with glass that if I shine visible light, it manages to shine right on through. If I shine UV radiation, which is going to be a shorter wavelength, it actually gets absorbed, and it gets absorbed because the frequency of UV radiation and the frequency in the molecules of the glass are the same. Remember, all materials have a natural frequency, and the natural frequency of glass tends to be very close to the frequency of UV radiation. And the result is it goes into vibrating those molecules, but it doesn't really get transmitted back through. Same thing what happens with infrared, but infrared's got an even longer wavelength. Infrared also gets absorbed. So the UV radiation is absorbed, the infrared radiation is absorbed, but the visible light will pass right through glass. So if your car window's rolled up and you're inside of it, you're probably not going to get a sunburn, even if the sun's shining on your left arm the whole time you're driving. You unroll that window, you hang your elbow out, you'll get a sunburn. But that glass blocks that UV radiation. The glass is also going to get really warm because the infrared radiation gets absorbed. So if all of the sun's energy just passed through the window wouldn't get hot. But the window's absorbing that heat radiation. This can also be true with different colors of materials. You may find that you've got a piece of glass. If this is blue glass, but transparent, then blue light is going to go right through it. I think I'm skipping ahead to the next chapter. But if you shine red light on it, red light has a longer wavelength. It absorbs the red light, and that causes a little bit of heating. It may also absorb green light or violet light because it's blue. Okay? So whether or not a material is transparent really does depend on the frequency of radiation. But what we think of being clear glass is transparent to all visible light. materials don't transmit light. You can't see through something that's opaque. So what does it do? Well, it can do two things. It absorbs light and it can reflect light. Now, most materials you know of are opaque. Okay. If you look at a blue shoe, it's reflecting blue light, but it's probably absorbing lots of other colors of light. Okay. Because opaque materials tend to absorb light, they also tend to have a little bit of thermal heating because of it. Oh, what about shadows? We get a shadow when something blocks the rays of light. You guys know if you go outside and you stand in the sunlight, you can see a shadow. Shadows can be very sharp or they can be kind of fuzzy around the edges, and it kind of depends on the light source. Generally, point sources form sharp shadows. Now, the sun isn't really a point source. The sun is huge, but the sun is so far away from the earth that it kind of behaves like a point source. So if you have a point source of light, and let's draw a little gingerbread man or something. I'll put a screen over here. Here's my point source. What's going to happen is the rays are going to spread out in all directions. And we're going to see a shadow. It's not a, oops, there we go. And that shadow will probably be fairly dark and fairly sharp. This very, very dark shadow is called an umbra. Now, if you have a big source of light, a big source of light acts like a lot of little point sources. So what happens is light from this point makes a shadow that looks like this. And we get a slightly different shadow. And light from right here makes a shadow that's a little different too. We pick a different point. And so it makes a slightly different shadow. And the result of these slightly different shadows is you get a light fuzzy area around the edge. This light fuzzy area around the edge is called a penumbra. Anytime you have a large source of light, or you have a source of light that's really close to the object, you're going to see some notable fuzziness around the edge of the shadow. It's not going to look sharp. If you have a very small source of light, or a source of light that's really, really far away, like the sun, it's so far away it seems like a small source, you get a nice sharp shadow. Probably the most interesting shadows are eclipses. There's two types of eclipse. There's a solar eclipse. Now, in a solar eclipse, the moon blocks the sun's rays. So here's the sun. It's way over here. It's huge. And then way over here somewhere, we've got a moon. And we've got the earth. Okay, so how does this work? Well, here's the sun's rays. And from that same point, here's the sun's rays. You can see it's going to create a shadow right here. But if we pick other points on the sun, there's the sun's rays. And there's the sun's rays. We're going to get that same idea of a fuzzy shadow on the edges. Right here, you're going to see a total solar eclipse. These people right here are not going to see the sun at all. But these people that are in, that's the umbra. That's a total eclipse. However, if you're in the penumbra, which is going to kind of look like a fuzzy area around that, you're going to see a partial eclipse. So when we see a solar eclipse, and those are fairly rare, the moon is blocking our view of the sun. But you have to be at just the right spot on the earth. Usually, like the last big solar eclipse we had, can't even remember whether, I guess it was a year ago last fall, almost 2 years ago now. If you were in the right part of North America, you got a total eclipse. If you were a little bit below, like we were, we saw a partial eclipse here in Texas. Okay. The other type of eclipse is a lunar eclipse. In a lunar eclipse, we have it the other way around. The earth blocks the sun's rays. So here's the sun. Here's the earth. And here's the moon. Now the moon is pretty small. And obviously this side, if we think about, this is the dark side of the earth. They're having night. This is the daytime side. We only see the moon at night because the sunlight is so bright, we can't see the moon during the daytime. But we can see that the sun's rays, no matter where we draw them, it's really easy for this moon to be in a total eclipse and be completely blocked out by the Earth's shadow. Okay. The reason, of course, is Earth has a really big shadow compared to the size of the moon. So, much more frequent to get a total lunar eclipse, but you have to be on the right side. It has to be nighttime in order to see it. The last thing I want to talk about just a little bit is the human eye. Human eye is really remarkable. The fact that we can see with such precision, the fact that we can see all these colors, the fact that the images are real images that are focused on the retina of our eye, but they're upside down, and our brain takes them and makes them right side up, is really pretty amazing. I am not an artist, but we'll try. Okay, so this outermost part on the front, this kind of bump that I do, is just a clear dome called the cornea. And the cornea starts bending the incoming light from all directions enough that we'll be able to focus it on this back part of the eye. This back part of the eye back here is like your movie screen. It's called the retina. Now, the colored part of your eye is the iris. And it's interesting to me because I didn't learn this till a few years ago. Blue eyes and brown eyes, green eyes, gray eyes, you don't have pigment in your iris. The only kind of pigment humans have is melatonin, if I say that right, and it makes your skin varying shades of brown, from very, 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 very palest color of beige to very, very dark. The blue, whether your eyes appear blue or brown or green, has to do with the structure of the iris itself and what colors of light it absorbs and what color of light it reflects. It's kind of interesting, but it's not actually colored blue with any type of pigment. The opening right here where the light can get through, that opening is called the pupil. That opening can be larger or smaller. It adjusts to the amount of light. In very bright light, the pupil will become very small and constricted to restrict the amount of light that's getting in. When it's really dark, the pupils will get really large. And then right behind the pupil is the lens. And then all in the middle here is this kind of jelly liquid called the vitreous humor. Humor, that's an O. All of this works together. The cornea, the lens, the vitreous humor, to act like a lens, very much like a camera lens, to focus images on the retina, which, like I said, is like the movie screen. Back here at the back somewhere, we have the optic nerve. That optic nerve takes those images from the retina and sends it to the brain, and they make pictures. Now, the retina itself is made up of two different types of, we'll call them antennae. They're sensors. There's rods. Rods are rod-shaped, and they help the most with seeing in dim light. If you're in very dim light, you probably are not going to see a lot of color, but your rods are going to let you make out shapes and forms. Okay. Cones allow us to see color, and the cones are concentrated more in the center of the retina. There are 3 different types of cones, and those 3 types of cones allow us to see any color in the rainbow. We're the only, well, I say we, primates are the only type of animal to have 3 different types of cones and see in all of these different colors, with the exception of one ground squirrel. I don't know why that ground squirrel is so lucky that it got 3 different types of cones and can see in all different colors, but it's kind of cool. Most animals, they only have rods, so they see in black and white. Or they may have 1 type of cone or 2 types, but they don't see in the full color spectrum that primates can see, and in particular humans can see. All right, we're going to talk a lot more about color in the next chapter, but this is the basics of light.